Everyone, I am Pushpita Chanda. I'm a PhD student at IIT Delhi. And I really am this So then they should be a reversal here. So why we introduced the Fresnel subperiodeal zone? Because the main goal is to examine the free propagation of spherical monochromatic wave emitted from a source. So we know that the mathematical description describing a harmonic spherical wave at a point P, uh, which has been like far away from a source, is given by that. And now we divide the wavefront in some angular regions for our mathematical expression. So see, so here you can see the here the point source is S. This is the point source, and all the this is from Hecht edition 5 optics book of Whitehead vision 5. There is a PDF available, free PDF. So whatever I'm saying, I'm not gonna write because it's like basically today's like module is very fast. So I'm just explaining and I'll write some key things, because today also most of the quiz is part of from the theory. There is not more of the mathematical expressions. So to examine the propagation of spherical monochromatic wave emitted from a point source is, and previously we know that when we are uh, from the previous discussion, we know that whenever we are considering Fresnel's diffraction, we are considering cylindrical or spherical wave. So this is the source is. If the Huygens first Fresnel's principle is correct, which should be able to add up the secondary wavelengths arriving at a point P and thus obtain the unobstructed primary wave. So our goal here is to examine the free propagation. So if there is no aperture or something else, there is no diffraction, then what would be the electric field at point P due to the point source S? So this is the wavefront. This is the wavefront, and we know that Huygens-Fresnel's principle is correct. Then the secondary wavelengths arriving at a point, they should add up. So in the process, we will gain some insight, and we also know some shortcomings and develop a few technique. So in this picture, you can say that spherical surface corresponding to primary wavefront at some arbitrary time t dash after it has been emitted from S at t is equal to 0, and the disturbance having a radius rho. This is the rho, and that's why the electric field, spherical electric field, has the term rho, that the primary wavefront has the radius of rho. Now we have divided the wavefront into number of angular regions. The boundaries of various regions corresponds to intersection of the wavefront with a series of spheres centered at P of radius r0 lambda by 2. So they are basically, we are assuming, actually it's not like this. First sphere is of the radius r0 plus lambda by 2. It's not a good approximation of the sphere, and the second sphere is go on like that. These spheres originating from the P and they have the intersection at here. So you can imagine the sphere. This sphere is far more vast having a radius r0, then r0 plus lambda by 2, then another lambda by 2. So the basic difference is lambda by 2, and that's why they are called half period zone, because the full period is lambda. So then there can be question why they are called half period zone. So the answer is due to that lambda by 2 difference. Okay. So here you can notice that for a secondary point source is one zone, there will be a point source in the adjacent zone that is farther from the P, like this point and this point. They are adjacent in the zone and they are lambda by 2 apart. And each zone is finite in extent. So now we move to this picture. So here that all the point we assume differential elementary area, which is basically ds. So you can assume this zone, this is the ds. Okay, this part is the ds. So all the point source within ds are coherent. So coherent, you need to remember that, because some questions are regarding this, if all the points are in one Fresnel zone are coherent or something. The basic assumption is that they will be coherent. So they are coherent, that means they are in phase with the primary wave. So we assume that secondary wavelets travel a distance r to reach P at a time t, and they are arriving at the same phase. So they will be arriving at omega t minus k rho plus r phase. Secondary wavelet. And the amplitude would be epsilon by rho. So the contribution to the optical disturbance at P from the secondary sources on ds is dE, and dE is k Ea by r of omega t minus k rho plus r into ds. Okay. So Ea basically is q epsilon naught rho. K is the obliquity factor. One plus cos theta, that you know. Okay. And we assume that for each Fresnel zone, assumption here, for each Fresnel zone, K is constant. So ds is, we know, rho d phi 2 pi into the sine phi. So this is basically rho square 2 pi rho square d phi. Then we can apply the cosine law and write r square is rho square plus rho plus r0 whole square minus 2. So remember the r is like this is r at this distance. There is the r. Okay. So for that we can write this rho plus r naught cos of 5, and this angle is 5. And doing all those calculation, it can be written as 2r dr is equal to 2 rho plus r naught sine 5 t5. Then we can put these values in ds. We can write 2 pi rho plus r naught r dr. And putting these values, we can assume that electric field, like when we take the integration, this is the disturbance arriving from the P from the LH zone is then KL. This is the obligative factor for LH. 2 pi EA rho plus R naught L minus 1 to RL, because we need to that from this R to this R or this R to this R. So basically we have like this cos omega t minus K rho plus R dr. So we know that RL minus 1 can be written as R naught plus L minus 1 lambda by 2, and RL can be written as R naught plus L lambda by 2. Because here you see the first term is from R naught plus lambda by 2, 1, then 2 into lambda by 2, then 3 into lambda by 2. So that's what. After doing all this calculation, we can get that EL for the electric field from the LH zone is minus 1 to the power L plus 1 to KL epsilon A rho lambda rho plus R naught sine omega t minus K rho plus R naught. So here you can see that if L is 0, then EL negative. If L is 1, then EL is positive quantity. So the sign changes between the positive and negative values depending on whether it is odd or even. So so for that reason, contribution from adjacent zones are out of phase and tend to cancel because they are almost equal to same. The obligative factor is crucial. So as L increases, theta increases and K also decreases. So the successive contribution do not in fact completely cancel each other. Something remain rest. And it is also interesting that EL by KL is independent of any position variables. Okay. And areas of each half period zone almost equal. Almost, not equal. Okay, they slightly increases. So so and also the average distance from each zone to P also increases. If their areas increases slightly, then there is increased number of emitters. So all cancel it out, and EL by KL is almost constant. So sum of the optical disturbance from all the emit zone at P is so E is equal to E1 plus E2 plus E3 and so on and so forth till EM. And then since they are in alternate signs, so this become E2 become minus, E3 plus, then this also minus and plus minus. If M is odd, then the series can be written like this: E1 by 2 plus E1 by 2 minus E2 plus E3 by 2 plus E3 by 2 minus E4 plus E5 by 2 and so on and so forth, or E as a E1 minus E2 by 2 minus 2 by 2 minus E3 plus E4 by 2 minus E4 by 2 minus E5 plus E6 by 2. So what is the purpose of doing this? The purpose of doing this is this becomes 0. This becomes 0. And here this becomes 0. Okay. So here the last term would be EM by 2. Here the last term would be minus EM minus 1 by 2 plus EM. So there is two possibilities, that either EL is greater than EL minus 1 plus EL plus 1 by 2, or EL is less than EL minus 1 plus EL plus 1 by 2. Okay. So it depends on basically K theta. How does that change? So obligative factor goes from 1 to 0 over many zones. So we can write that En almost is equal to E2 and EM minus 1 is almost equal to EM. So if we follow this notation, then E becomes E1 by 2 plus EM by 2 is less than. Or if we follow the second command, this command, so that is E is greater than E1 minus E2 by 2 minus EM minus 1 by 2 plus EM. So whatever the reason, when you like approximate like this, E1 is almost equal to E2, E minus 1 is almost equal to EF. The conclusion is that E is almost equal to E1 by 2 plus En by 2. That's the conclusion. And either this or that. And also due to obliquity K, Em is almost equal to 0. So E is basically E1 by 2. Okay. So these are all done when M is odd. Okay, remember that. So at last E became Kn1 is sin omega t minus K rho plus 1. Okay. So why we are assuming M is like odd? Because to do this thing. Now, once we have get the electric field of the free propagation of the spherical monochromatic wave, now we can move to the like another important fact. If then we that is the vibration curve. So these are both the example of the vibration curve. And why this is important? So for vibration curve, to imagine what is the vibration curve, it is a graphical method for qualitatively analyzing a number of diffraction problems that arise prominently from the circularly symmetric configuration. So for that, each Fresnel zone is divided into has been divided into n subzones by intersection of spheres, and their m subzones are basically r2 lambda by 2n. The first zone we are talking about, the first zone up to that. This is for first zone, this is for second zone, this is for third zone, and so on and so forth. So each subzone contributes to the disturbance at P, the resultant of which, of course, is E1, just E1. Whatever we are doing, that is gonna be E1 by 2. Since the phase difference across the entire zone from 0 is to its edge is pi rad, because this 2 pi, when wave goes lambda distance, the phase difference is 2 pi. So when that is lambda by 2 distance, that is pi rad. So this is pi rad. This is also pi. So the east subzone is divided by pi by n rad. Then if we have the vector addition, we get the picture something like this. And this is for n is equal to 10, the vibration. And these are all phasors. And you can see that when we draw the tangent, the curve doesn't follow the full circle. It comes short. The polygon of vectors blends into a segment of a smooth spiral called the vibration curve. Okay. For each additional Fresnel zone, the vibration curve swings through one half turn. So from here, you see that this is OS. Okay. This is the first Fresnel zone. Then when second Fresnel zone comes, this is the second Fresnel zone. This is the third Fresnel zone, and so on and so forth. And they and they are like spiral. They don't complete a circle. That's why they are called vibration curve, not vibration cycle. So the radius for each zone in the vibration curve is proportional to the square root of the numerical designation, that is m. So radius of the 100th zone will be 10 times that of the first zone in the Fresnel zone. Okay. And also we know that accordingly obligative factor that decrease rapidly for first few zones, then they like decrease more in a slow way. So this is the vibration. So now we can move to the circular apertures for the spherical waves. So we'll see, this is basically this is actually wavefront, and there is the corresponding vibration curve, and here we put the circular aperture. Okay. The Fresnel's procedure we have like put into like to deduce the first unobstructed free flowing wavefront, what will be the electric field. We can do the same approach for here also, but here with the aperture. So when we do that, then we let's envision a monochromatic spherical wave impinging on a screen containing a small hole. This is the screen. This is the sigma. Okay, we first record the irradiance arriving at a very small sensor placed at point P. This is P on the symmetry axis. Our intention is to move the sensor around in space and to get a point-by-point map of the gradients of the region beyond the screen. This is the source, this is the circular aperture, but we need to assume that the wavefront is like flowing through the aperture. So now also the P will show that integral number of zone is filling the aperture. So if M is even, then E is equal to E1 minus E2. That will cancel out. E3, and they are all not. The values are not. And so on and so forth. En minus 1 minus En. So based on that, E will be 0. And that would happen same for if we would have calculated for the freely flowing like spherical obstructive. If M is odd, then we are in the game. Then E becomes E1. If this is odd, then you can write it like this. And so on and so forth. Then E is E1. So we see that when there is no aperture, E was E1 by 2. Now it is E1, that is almost double. And so that means that if we put a aperture, we get more irradiance. And the irradiance become 4 times the actual irradiance if there would not be any aperture. That's the thing. So now we will see what will be the vibration curve for that. Okay. So for this curve, the A, the hole is very small. Only 1/2 of the Fresnel zone, first Fresnel zone appears within it. Half of first Fresnel zone appear through the hole. So we have seen that it doesn't matter how many Fresnel zones appear through the circle or aperture. That's the thing, basically. We only worried about the one, but we'll see that when the P moves along the way, here the P is at the symmetry axis, the irradiance may be equal to E1, but the pattern is not. The pattern does change. So hole is very small and only about 1/2 of the first Fresnel zones appears within it. The length of the phasor is this here in the vibration curve. Okay, this is the length of the phasor. So you have seen that this is A. This is the A. So here we denote as OSA as like this. And this corresponds to field amplitude. And now hole gets a bit bigger. Now it got 3/4 of first Fresnel zone. So see, this is up to first Fresnel zone. So this is actually 3/4 of the first Fresnel zone. Remember, it is up to the outer circle, not the inner circle one, because the first outer circle is corresponds to first Fresnel zone. Then it goes round into it. Okay, then we see that, and here entire first Fresnel zone is like appears within the hole. So this is the phasor up to like this. Okay. And this phasor OS and AX is the maximum on the electric field. Increasing the size of the hole will subsequently decrease the phasor and the radiance on it, because we can see this is the maximum. This OSS is the maximum. If we increase the hole, irradiance will decrease. That's the key thing. Now we'll see what will happen when we basically move. So when we move P from the P1, P2, P3, okay, to get the idea what will happen, we need an approximation term, which is the number of zones, which is also called Fresnel number, which is NF. How many number of zones are in the aperture? And that is basically pi r square by A. A is the area of each zone, and pi r square is this is basically R. Okay. So basically, for the purpose of the sense, so if the point source and A is also given by an equation, that is A is rho plus R naught. So this distance is rho, this distance is R. Okay. So if rho is 1 meter and R naught is 1 meter, this is R naught basically. Lambda is 500 nanometer, and there are 4 zones when R is equal to 1 nanometer. And when R is equal to 1 centimeter, there are 400 zones. So that means there is NF is 4 and there NF is 400. Okay. When NF become less than 1, this all things goes to Fraunhofer diffraction. So just imagine that at Fraunhofer diffraction, your R naught is very, very far away. Okay, so you will see even not one Fresnel zone. That is when Fraunhofer diffraction kicks in. When NF is equal to 1, then equal to or greater than 1, then we get Fresnel diffraction. So see here that this is for P. P will see this kind of Fresnel zone. P1 see that first Fresnel zone is there still. So here you can see two zones. Two zones. Here we can see second zone has been partially obscured and third begins to show. Here in P2 we see first zone is there, second is not full, third part of that there, fourth is beginning to show up, and when it moves to P3 it says like this. So here you see that contribution of phase 1 and phase like Fresnel zone 1 and Fresnel zone 3 are in phase. It gets a bright spot. As it moves slowly outward, the portion of the successive zones are the sensor dictative series of relative maxima and minima. So what does the sensor says? The sensor sees like this. This is what sensor sees. So this is the diffraction pattern. Of circular aperture. Of increasing size. So when you shift the aperture, it's the sensor's position is being shifted. Position is changed. Here the size of the aperture change. So then the aperture first we will see only the bright spot, then a dark spot in the came, then a bright spot inside the dark spots came. Like Newton's ring. So how this is how it's gonna see. You can, and this is the normalized radiance number of Fresnel zone. When there is one Fresnel zone, you get maximum radiance. So when 2 and 3 Fresnel zones come, then when 2 Fresnel zone came, then they are the opposite in phase, it is 0. When 3 come, there is some kind of intensity. When there are 4, they always cancel out. Then at fifth, you will get some zones. So these are the normalized irradiance at on axis point P that is moving toward O. Now, there are now we go to plane waves. Circular aperture, but plane wave. Then the system will see like this. Okay, the plane waves is emerging through this circular aperture. So here rho tends to infinity, and so this is the three-dimensional irradiance distribution. Basically, what we'll see. Solution, this unit are in r square by lambda. So where r is the radius of the hole, this is the r. Okay. So here aperture extends from +1 to -1 at a distance of r square plus lambda is equal to r naught. One Fresnel zone fills the aperture and the irradiance has a maximum. Here we can see. Beyond that, irradiance falls off monochromatically until it reaches the far field region. The first four zones of the distribution, this is the Fresnel, this corresponds to first Fresnel zone, this corresponds to second Fresnel zone, this fourth Fresnel zone. Okay, now we go to circular obstacle. So for circular obstacles, we got reflection pattern like this. So when there is a circular obstacle, it depends on that how much it covers. And it looks like diffraction pattern looks like this. It covers the Fresnel zone. So if it precisely covers the first Fresnel zone, then its contribution of E1 is subtracted, then E becomes E1 by 2 minus E1. So 1 Fresnel zone. when it's become minus A1/2. And that just like give you the Poisson's spot. But so this is the irradiance on the central axis, generally only slightly less than the unobstructed Earth. There is a bright spot everywhere along the central axis, except immediately behind the circular obstacle, and that is called Poisson spot. So, and this existence of Poisson spot is a very big blow to the Earth theory. So, then come Fresnel's zone plates. You can see here also the Poisson spots. So Poisson spots. This is also Poisson spot. So they are with we basically we have seen that the each Fresnel zone contribute like in have opposite signs. The electric field has opposite signs of the is zones. So if we can somehow make in phase, then they will add up. So for that, if a plate that alters the light in every other half period zone, that is called Fresnel's zone plate. So using that, we can do that. And it have a primary focal length F1 is equal to Rn squared by n lambda. So basically, this is the picture for that. It's F1. And this is basically zone plate geometry. And how we come to this number is from that wave that travels the path in this path arrive out of phase by m lambda by 2 of this path. So rho m by Rn, this is rho m, this is Rn, minus rho naught plus R naught equal to m lambda by 2. And rho m is root over Rn square plus rho square. Similarly, Rm is equal to root over Rn square plus h naught square. So binomial theorem, rho m becomes rho naught plus Rn square by 2 R naught, and Rn becomes R naught plus Rn square divided. And now we substitute that here, equation 1. By rho naught by 1 by R naught is equal to m lambda by Rn square. For plane wave, rho naught is infinite the assumption, so Rn square is equal to m R naught lambda. And for focal length, from this we got f1 is equal to Rn square by m lambda. So there is in the class there has been discussion about rectangular aperture. This is the rectangular aperture, and this is a pretty vast discussion. Then this concept is also described in the class, that is orno spiral, and how that is like written, what is the mathematical form there. It is actually a complex plane that you need to remember. Okay, complex plane, and from this Kronos spiral we can know how it will like how the amplitude will behave, and where will be the spot for quantitative determination of the diffraction pattern. From the single slit, single slit Fresnel's diffraction fraction. This is the corresponding Kronos spiral and the diffraction pattern. This is the diffraction pattern by narrow obstacle. This picture corresponds to Babinet's principle. So the two diffracting screens are said to be complementary when the transparent region one exactly correspond with the opaque region on the other and vice versa. And when two such screens are overlapped, its combination is obviously completely opaque. And that is actually Babinet's principle. Which is E1 plus E2 is equal to EU. So for these things, the rectangular aperture, corner spiral, then the Fresnel's diffraction by single slit, and the Babinet's principle, diffraction pattern of the narrow obstacle, they have been discussed well in the class, and I'm not going to discuss all this. Now I will go to the questions. Now we discuss some previous year quiz question. The obliquity factor. It can vary from which range? Answers are I have shown that cos theta varies from 1 to -1. So this is varies 2 to 0. So half of that 1 to 0. That's the answer. Question 2 is the inclination or directionality of secondary source is expressed by one secondary source is expressed by so the answer is obliquity factor. No sign, no, not sine, not cosine, no directional ratio, obliquity factor. Question 3. All the point sources within the area of a Fresnel zone are Schumann covalent. Option B is incovalent. Option C is partially covalent. It's independent. So point sources from one Fresnel zone is originated from the same primary source. So they are basically covalent. Question 4. The minimum value kitting indicates So the minimum value is 0, K min, which is half of cos theta plus 1. So when theta is 180 degree, that happens. That means when theta is 180 degree, the obligative factor is 0, and that means no backward propagation. 180 degree is actually the backward. Question 5. Zone is also known as we know that is half period zone. Why? Because the zones are divided by like this. Period is lambda. Lambda by 2 is half period. Question 6. If a Fresnel zone is divided into 5 subzones, the phase of each subzone will be. So, one full zone, which is half period zone, is pi. So pi by 5, because the subzone is zone is divided into 5 subzones, so that would be 5 pi by 5. Question 7. The last Fresnel zone does not contribute to the vibration curve because options are its amplitude is 0, obligative factor is 0, phase is undefined, it cancels completely. So we know it goes to 0 because of the obligative factor is 0. The Fraunhofer diffraction pattern is observed Fresnel number is. I have discussed it just few minutes before, that is when it is less than equal to 1. When it is greater than or equal to, not equal to 1. When it is equal to 1, it is Fresnel diffraction. When it is greater than 1, it is also Fresnel diffraction. Question 10 is, as we move away from the aperture, wait, this is 9. Fresnel zone decreases, increases, remains constant, becomes infinite. So when we move away from the aperture, fewer zone fits inside the aperture. So basically, when we go from Fresnel to Fraunhofer, we see that the Fresnel number decreases. That means that number of zone fit in the aperture decreases. So the answer is decreases. Then input path screen now contains aperture 2.00 millimeter in diameter, a monochromatic point source lambda naught is equal to 550 nanometer lies on the axis running through the detector to the center. So the center of the aperture perpendicular to sigma. The source is 3 meter in front of sigma and point P is 3 meter beyond it. On the central axis. Calculate the number of Fresnel's zones that fill the whole hole as seen from P. Will there be a so NF is basically area that would be rho r0 r square by rho r naught. Here rho is 3 meter, r naught is equal to 3 meter. Capital R is 2 meter, 2 millimeter. Lambda is 550 nanometer. Now if we put all of this NF became 4.8. So if N were P zones, 5, then P would be bright spot. Here NF is equal to 4.8. Here it would be fairly bright spot. Here we see NF is greater than 1, so it would be a Fresnel diffraction. We can also see from this equation, which is relation R must be greater than S squared by lambda for Fraunhofer. So here S squared by lambda 7.3 meter and R is 2 millimeter. So here also you get that R is less than S squared by lambda. So Fresnel diffraction will take place. So this kind of question will come in the quiz, and if another question is question 11, the primary focal length of a zone plate is to be 200 centimeter using 500 nanometer light. The plate must be slightly larger than 10 millimeter in diameter. How many transparent content? So F1 is equal to Rm square by m lambda. M is equal to Rm square by F1 lambda. Putting all those value, Rm is 10 millimeter, 10 to the power minus 3 whole square into 500 10 to the power minus 9. Here F1 is 200 centimeter 10 to the power minus 2. 100. So apparently 100 transparent zones will be there. So this kind of question will appear. So that is for today. Next class we will dive into polarization. Thank you.